everybody, and welcome to another ASMR video here on the channel. In tonight's video we have episode number 2 of our series Let's Learn About Space. I can't actually remember, now I'm thinking about it, what episode 1 was. Was it our solar system? Oh no, it was the Milky Way. It was the Milky Way. And I've got a bit of a list that we're going to work our way through, involving and focusing on different elements to do with outer space. And I had a few comments from you guys as well, and I have updated that list, so thank you for your recommendations. But tonight we are going to be taking a look at black holes. Essentially going to be looking at what they are, how they're made, how they're discovered, and then also taking a look at some of the most sort of insane black holes that have been discovered and exist today. So hopefully you enjoy, hopefully you find it informative and relaxing as always. And without further ado, let's get into it. So, a black hole is a cosmic body of extremely intense gravity from which nothing, not even light, can escape. A black hole can be formed by the death of a massive star. When such a star has exhausted the internal thermonuclear fuels in its core at the end of its life, the core becomes unstable and gravitationally collapses inward upon itself, and the star's outer layers are blown away. The crushing weight of constituent matter falling from all sides compresses the dying star to a point of zero volume and infinite density called the singularity. We will kind of take a look at some of the terms to do with black holes and properly break them down. Details of the structure of a black hole are calculated from Albert Einstein's general theory of relativity. The singularity constitutes the center of a black hole and is hidden by the object's surface, the event horizon. Inside the event horizon, the escape velocity, and that's the velocity required for matter to escape from the gravitational field of a cosmic object. The escape velocity exceeds the speed of light, so that not even rays of light can escape into space. The radius of the event horizon is called the Schwarzschild radius, after the German astronomer Karl Schwarzschild, who in 1916 predicted the existence of collapsed stellar bodies that emit no radiation. The size of the Schwarzschild radius is proportional to the mass of the collapsing star. For a black hole with a mass 10 times as great as that of the Sun, the radius would be 30 kilometers. Only the most massive stars, those of more than 3 solar masses, become black holes at the end of their lives. Stars with a smaller amount of mass evolve into less compressed bodies, either white dwarfs or neutron stars. Black holes usually cannot be observed directly on account of both their small size and the fact they emit no light. They can be observed, however, by the effects of their enormous gravitational fields on nearby matter. For example, if a black hole is a member of a binary star system, matter flowing into it from its companion becomes intensely heated and then radiates X-rays copiously before entering the event horizon of the black hole and disappearing forever. One of the component stars of the binary X-ray system, Cygnus X1, is a black hole. Discovered in 1971 in the constellation Cygnus, this binary consists of a blue supergiant and an invisible companion 14.8 times the mass of the Sun that revolve about one another in a period of 5.6 days. Some black holes apparently have non-stellar origins. Various astronomers have speculated that large volumes of interstellar gas collect and collapse into supermassive black holes at the centers of quasars and galaxies. A mass of gas falling rapidly into a black hole is estimated to give off more than 100 times as much energy as is released by the identical amount of mass through nuclear fusion. Accordingly, the collapse of millions or billions of solar masses of interstellar gas under gravitational force into a large black hole would account for the enormous energy output of quasars and certain galactic systems. One such supermassive black hole, Sagittarius A star, exists at the center of the Milky Way galaxy. Observations of stars orbiting the position of Sagittarius A star demonstrate the presence of a black hole with a mass equivalent to more than 4 million suns. Supermassive black holes have been detected in other galaxies as well. In 2017, the Event Horizon Telescope obtained an image of the supermassive black hole at the center of the M87 galaxy. That black hole has a mass equal to 6.5 billion suns, but is only 38 billion kilometers across. It was the first black hole to be imaged directly. The existence of even larger black holes, each with a mass equal to 10 billion suns, can be inferred from the energetic effects on gas swirling at extremely high velocities around the center of NGC 3842 and NGC 4889, galaxies near the Milky Way. The existence of another kind of non-stellar black holes proposed by the British astrophysicist Stephen Hawking. According to Hawking's theory, numerous tiny primordial black holes might have been created during the Big Bang, a state of extremely high temperatures and density in which the universe originated 13.8 billion years ago. These so-called mini black holes, like the more massive variety, lose mass over time through Hawking radiation and disappear. If certain theories of the universe that require extra dimensions are correct, the Large Hadron Collider could produce significant numbers of mini black holes. So we mentioned a couple of terms there. We're now going to kind of break down what they are so we can better understand exactly what a black hole is. So we begin with event horizon. So an event horizon is the boundary marking the limits of a black hole. At the event horizon, the escape velocity is equal to the speed of light. Since general relativity states that nothing can travel faster than the speed of light, nothing inside the event horizon can ever cross the boundary and escape beyond it, including light. Thus, nothing that enters a black hole can get out or can be observed from outside the event horizon. Likewise, any radiation generated inside the horizon can never escape beyond. For a non-rotating black hole, the Schwarz horizon. Rotating black holes have distorted, non-spherical event horizons. Since the event horizon is not a material surface, but rather merely a mathematically defined demarcation boundary, nothing prevents matter or radiation from entering a black hole, only from exiting one. Our next term is singularity. Singularity is a theoretical condition that could arise in the near future when a synthesis of several powerful new technologies will radically change the realities in which we find ourselves in an unpredictable manner. Most notably, the singularity would involve computer programs becoming so advanced that artificial intelligence transcends human intelligence, potentially erasing the boundary between humanity and computers. Often, nanotechnology is included as one of the key technologies that will make the singularity happen. And we briefly touched on them, but what is a supermassive black hole? It's an incredible song by Muse for a start, but really, it is a black hole that is more than 100,000 times the mass of the Sun. Nearly every large galaxy has a supermassive black hole at its center. Active galactic nuclei, such as Seyfert galaxies and quasars, are powered by supermassive black holes. The largest supermassive black hole is in the galaxy cluster Abell 1201 and has a mass 30 billion times that of the Sun. Sagittarius A star, the supermassive black hole at the center of the Milky Way galaxy, has a mass 4 million times that of the Sun. The discovery of supermassive black holes was a consequence of the investigation of quasars in the mid-20th century. In the earlier surveys of the sky at radio wavelengths in the 1950s, many radio sources were found to coincide with previously known galaxies, but some coincided with blue, star-like objects, which sometimes had fuzzy halos. These objects were called quasi-stellar radio sources, or quasars for short. These objects were called quasi-stellar radio sources, or quasars for short. I could be saying quasar completely wrong. Quasar? I don't know, feel free to abuse me in the comments. Observations of quasar 3C273 by the Dutch-American astronomer Martin Schmidt showed that the quasars were the more distant objects known, and thus brighter than any known galaxy. Quasars were also observed to vary in brightness over a period of days, which meant that they were actually extremely small. Since a quasar is so compact and so luminous, the radiation pressure inside it must be huge. Indeed, the only way a quasar can keep from blowing itself up with its own radiation is if it is very massive, at least 1 million solar masses, if it is not to exceed the Eddington limit, the minimum mass at which the outward radiation pressure is balanced by the inward pull of gravity. Quasars represented a previously unknown kind of object, one that was roughly the size of the solar system, but with a mass 1 million times that of the Sun, and brighter than a galaxy. Shortly after Schmidt's discovery, the mechanism powering quasars, accretion of matter by gravity onto supermassive black holes, was independently proposed by Russian astronomers Yakov 1965, scientists had recognized that quasars are part of a much larger population of unusually blue sources, most of which are much weaker radio sources, due faint to have been detected in the early radio surveys. The larger population, having all the properties of quasars except extreme radio luminosity, became known as quasi-stellar objects, or simply QSOs. Since the early 1980s, most astronomers have regarded QSOs as the high luminosity variety of an even larger population of active galactic nuclei, or AGNs. Each of these objects contains a supermassive black hole. As matter falls toward the supermassive black hole, it forms an accretion disk because the matter being accreted possesses rotational or angular momentum sufficient to prevent it from simply falling inward toward the accretor along a straight line. Matter within the disk spirals inward because it loses energy and angular momentum due to turbulence and viscosity. Because the disk material has to lose energy to accrete onto the central object, the material gets hot, and the heat generated escapes through both sides of the disk. The temperatures of the accretion disks reach up to several million kelvins. Therefore, the disk emits light from infrared to X-ray wavelengths. Supermassive black holes formed in the early universe and have evolved together with galaxies since then. Exactly how such black holes formed is unknown, but their growth must have been rapid, since supermassive black holes have been observed in objects that formed about 1 billion years after the Big Bang. So, the next question we're going to address is, how were black holes discovered? The first inkling that anyone had about black holes came in 1930, when young astrophysicist Subramanian Chandrasekhar was mulling over the consequences of several recent discoveries, including Einstein's theory of special relativity. He calculated that all stars larger than 1.4 times the mass of our Sun would eventually run out of fuel and collapse. Scientists at the time were shocked and skeptical. The most famous astrophysicist at the time, Arthur Eddington, publicly trashed the idea at a gathering, saying, "I think there should be a law of nature to prevent a star from behaving in this absurd way." However, the damage was done. Once the astrophysics community had come to grips with a calculation performed by a 19-year-old student sailing off to graduate school, the heavens could never again be seen as a perfect and tranquil dominion, physicist Freeman Dyson later wrote. Scientists soon worked out that other laws, including Einstein's theory of general relativity, required black holes to exist. The idea became increasingly accepted. In the latter half of the 20th century, eminent theoretical scientists, including Stephen Hawking, John Wheeler, and Jacob Berenstein, and many others, explored the details of the mathematics and physics behind black holes. Meanwhile, evidence from telescopes began to pile up that black holes were in fact out there in the universe. In the 1960s, quasars were discovered, faraway objects that were emitting such strong radiation that there was no explanation other than gigantic black holes chewing up and spitting out matter. Throughout the 1990s, scientists including Andre Gears and Reinhard Genzel precisely tracked the movements of stars around the center of our galaxy, proving they were orbiting around something invisible but so massive that it had to be a black hole. They would go on to receive the Nobel Prize in 2020 for this work. Then in 2015, two special detectors known as the Laser Interferometer Gravitational Wave Observatory, really rolls off the tongue, picked up the ripples from a pair of black holes colliding. They have since detected nearly 100 such collisions. In 2019, the Event Horizon Telescope, a collection of telescopes around the world acting in concert, was able to take an image of the gas swirling around a gigantic black hole in another galaxy. They followed this in 2022 with an image of our own black hole, the one that sits in the centre of the Milky Way, and we are making more discoveries all the time. So, how was the first picture of a black hole taken? In 2019, people around the world were thrilled to see the first image ever taken of a black hole. And then in 2022, an image of our own personal supermassive black hole in the Milky Way. The bright ring around each one is created by material glowing very hot as it circles the black hole. This was the first direct image of a black hole ever taken. All of the other pictures you've seen are simulations or artist illustrations, or in Interstellar. These black holes are so far away that no normal telescope would ever be powerful enough to see them. You would need a telescope the size of the Earth. But scientists figured out they could piece together images taken simultaneously from telescopes situated all around the Earth instead. One of these was the South Pole Telescope, run by a collaboration headed by the University of Chicago, which provided the view from the bottom of the Earth. Altogether, this network of combined telescopes is referred to as the Event Horizon Telescope. They next hope to create a movie of the glowing gas moving around a black hole as it's pulled in. So here's a good question: what do scientists still not know about black holes? Even as new detectors and telescopes have been able to tell us more and more about black holes in the past decades, scientists still have hundreds of questions about black holes. What do they eat and how often? What happens as stuff falls in? When it falls in, how much comes back out? Does this stuff end up causing the black hole to spin? How are these black holes created in the first place? There are more fundamental questions too, ranging from what's inside a black hole to how are supermassive black holes tied to their galaxies. Everything about black holes is absurd. It's very appealing to say they can't possibly exist, except that both our theories and our observations show that they must and in fact do exist. That's a quote from Professor Holtz. One thing that keeps scientists awake at night is whether information that falls into a black hole is truly gone forever. There are other laws of physics that say that all information in the universe is preserved. Even if you burn a notebook, its information could theoretically be recovered from the traces and gases that are left behind, as well as the light that was emitted. But as far as we can tell, it's possible that the information within a notebook dropped into a black hole could be truly erased from the universe. So, to finish this video up, we're now going to run through a list of the most insane black holes that exist today. My throat's making some very strange noises, I do apologise. I've tried to cut around it where possible. So we begin with the biggest black holes. Nearly all galaxies are thought to harbour at their cores supermassive black holes, millions to billions of times the mass of Earth's Sun. In 2011, scientists discovered the largest black holes known is known as NGC 3842, the brightest galaxy in the Neo cluster, nearly 320 million light-years away, has a central black hole containing 9.7 billion solar masses. The other, NGC 4889, the brightest galaxy in the Coma cluster, more than 335 million light-years away, has a black hole of comparable or larger mass. The gravitational range or event horizon of these black holes is about 5 times the distance from the Sun to Pluto. For comparison, these black holes are 2,500 times as massive as the black hole at the centre of the Milky Way galaxy, whose event horizon is 1/5 the orbit of Mercury. But what about the smallest black hole? The smallest black hole discovered to date may be less than 3 times the mass of our Sun. This would put this little monster, officially called IGR J17091-3624, again really rolls off the tongue, near the theoretical minimum limit needed for a black hole to be stable. As tiny as this black hole may be, it looks fierce, capable of 20 million miles per hour winds, the fastest yet observed from a stellar mass black hole by nearly 10 times. This next section says, cannibalistic black holes. Black holes devour anything unlucky enough to drift too close, including other black holes. Scientists recently detected the monstrous black hole at the heart of one galaxy, getting consumed by a still larger black hole in another. The discovery was the first of its kind. Astronomers had witnessed the final stages of the merging of galaxies of equal mass, so-called major mergers, but minor mergers between galaxies and smaller companions had long eluded researchers. Using NASA's Chandra X-ray Observatory, investigators detected 2 black holes at the center of a galaxy dubbed NGC 3393, with one black hole about 30 million times the mass of the Sun, and the other about 1 million times the Sun's mass, separated from each other by only 490 light-years. Here we have the bullet-shooting black hole. Black holes are known for sucking in matter, but researchers find they can shoot it out as well. Observations of a black hole called H1743-322, which harbours 5 to 10 times the mass of the Sun and is located about 28,000 light-years from Earth, revealed it apparently pulled matter off a companion star, then spat some of it back out as gigantic bullets of gas, moving at nearly a quarter of the speed of light. You have the oldest known black hole, the oldest black hole found yet, officially known as ULAS J1342 plus 0928, was born about 690 million years after the Big Bang. The ancient age of this black hole actually poses some problems for astronomers. This brilliant enigma appears to be 1 billion times the mass of the Sun. How black holes became so massive so soon after the Big Bang is difficult to explain. And we finish with the brightest black hole. Although the gravitational pulls of black holes are so strong that even light cannot escape, they also make up the heart of quasars, the most luminous, most powerful, and most energetic objects in the universe. as supermassive black holes at the centers of galaxies suck in surrounding dust and gas, they can spew out huge amounts of energy. The brightest quasar identified to date lies about 12.8 billion light years away from Earth. They're just so fascinating, aren't they? Like, I'd say they're probably the thing I'm most fascinated with when it comes to outer space topics. And I think I can't blame scientists for staying up late at night, because I don't know if we'll ever truly know what it's like to be inside a black hole. Hey, maybe Interstellar's right. Maybe what happens in that amazing movie is the God's honest truth. But